So, we finished up last time with this sort of magnificent result that allows you to avoid doing integrals by. So, so we ended up with the fundamental theorem of calculus 2, right? And that's really if somebody gives you a function, say f of x is sine x, and says what is the definite integral from 0 to pi of sine x. Right. So normally the way you have to do it is to say, well, I'm going to take partitions of my integral, and then I'm going to take Riemann sums on those guys, and then I'm going to take the limit of those Riemann sums as the partitions become infinitely fine, and see what number that tends to. Right. So it's a big hassle, but the fundamental theorem of calculus says that you don't have to do that. Right. It says all you need to do is find an antiderivative. Right. Well, what does it say? Can somebody tell me what the fundamental theorem of calculus says? What is it? Somebody who doesn't normally talk about that. How about you, Mr. Yeah, where f is what? You find antiderivative. That's it. You find some antiderivative, right? In this case, negative cosine is an antiderivative. Right? Negative cosine is an antiderivative, so you take negative cosine and you take the difference at the endpoint, that's negative cosine of pi minus negative cosine of 0. Right? Let's see, cosine of pi is negative 1, right? So we get negative 1, and then minus, so plus 1 is 2. So the area under there is 2. Okay, so that's great. Okay. So okay. So let me quickly sketch out why we believe this. Why is this true? Why is it true that the integral from a to b of f is f of b minus f of a, where f is any antiderivative of little f for f continuous? Why is it true? One way of saying it, this is sort of cool. I wasn't planning to do this, but I think I'll do it because it's cool. One way of thinking about this is to use the mean value theorem. And actually, you can see it from the mean value theorem. Say, okay, look, if I have my function, right, on a, b, and I chop this thing up into some partition, right, x0, x1, x2, xn. I chop this thing up into subintervals, right? On each interval, right, let's look at one of these intervals, x of I minus 1, comma x of I. Okay, let's choose one of these intervals, x of I minus 1, comma x of I. What does the mean value theorem tell you? What does the mean value theorem tell you? Well, it says, mean value theorem says about the antiderivative that, does anyone remember? What does the mean value theorem tell you? The most important theorem. Go ahead, Tim.
Well, I don't know what it is with the antiderivative, but I know it's just
say it again?
I know it's, I don't know if this is about the antiderivative.
Well, let's just apply the mean value theorem to the antiderivative. What does it say about the antiderivative? Right?
Say that f prime of x equals a over b minus a.
Okay, so f of b minus f of a over b minus a, right? Oops, over b minus a, right? Equals. I'm gonna apply it to big F. Right? You can apply the mean value thing to whatever function you feel like, as long as it's continuous and differentiable, right? As long as it satisfies the conditions. Are you saying that I can't use it on big F because I have a capital letter instead of a lowercase letter? Right? No, right? You can mean value theorem applies to any function that satisfies these conditions.
That's f that's drawn, right?
That's F that's drawn, but I'm going to apply the mean value theorem to big F. Okay. Okay. So, and you'll see why in a second. Yeah. Okay. So what does it say? That there's some point inside where for some S1 inside the interval. Right? There's some S1. There's some point inside the interval where this holds true. Everyone, anyone confused at this point? Everyone following? Yeah.
Can you indicate where the xi minus 1 are on that graph?
Right here. So we just choose one interval, x of I minus 1, x of I, and there's going to be some si inside there. Okay. Okay, so that's true. So what does that say? That says that f of xi minus f of xi minus 1 equals f prime si times xi times I minus 1. Right. Just multiplying through by the denominator, I get this, I get this. And that's true for every interval. Xi minus 1. That's true for every interval. It's true for the first interval, it's true for the second interval, etc., etc. Right? So like for the first interval, what am I going to get? I'm going to get f of x1 minus f of x0 equals f prime s1 times delta x. Right, remember that this thing is delta x. Okay, call it delta x. Right, it's true for the second interval. F of x2 minus f of x1 equals f prime at some point s2 times delta x. Right? It's true for the third interval, for the fourth, for the fifth, for all the intervals, right? Up to the last one, f of xn minus f of xn minus 1 equals f prime s n delta x. Everyone all right? Everyone all right? Anyone confused? No? Okay. Right. So we applied the mean value theorem to the antiderivative guy on each subinterval, and then we said, what does that tell us? That tells us a fact about each subinterval. Now we're going to do something crazy, which is we're going to add up all those facts. Okay. We're going to add up all these things together. So what do we get on the left-hand side? When we add all this stuff on the left-hand side, the sum of everything on the left-hand side will be the sum of everything on the right-hand side. Does anyone see what happens when you take the sum of the left-hand side? Something sort of cool happens. Victor?
Well, when you take the sum of all the intervals, you're just going to get the distance between b and a, or between f and b and f of a. So f of b minus f of a.
Right. So you look what happens. You get f of x1 minus f of x0, f of x2 minus f of x1. Right? So these things will become 0. These things cancel out. Right? You get f of x3 minus f of x2. So f of x2, you get a negative f of x2 and a positive f of x2. You get 0. 0, 0, 0, 0, 0, 0, 0. Right? All these things, diagonal guys, will cancel out. And what you're left up with the end is f of xn minus f of x0. Right? That's to say f of b minus f of a. Equals f of b minus f of a. Right? And what does it say? F of b minus f of a is equal to this Riemann sum. I'm sorry. F prime. What's f big F prime? F big F was the antiderivative of little f. So what's big F prime? Little. Right? So be little f evaluated at Si delta x from I equals 1 to n. Right? So you see, right, f of b minus f of a equals the Riemann sum as I equals 1 and the Riemann sum of little f. Right. So now let n go to infinity. What happens to the left-hand side? Nothing. Right. You still stay. It's f of b minus f of a. What happens to the right-hand side? If you take the limit of Riemann sums for your function, you end up with the integral. You end up with the integral. That's it, right? The difference of the sum, the difference of the at the endpoints of the antiderivative is the definite integral of the function. Go ahead. You have a question. Do you have a question?
Yeah, I have a couple.
Yeah, okay.
I had thought on the homework last night in regards to this.
Yeah.
I thought there were portions where we had to take the antiderivative both f of the little antiderivative, the whole function of the median a to get the definite integral.
Yes, yes.
What you put on the board is that we don't have to, that we have to take like actually f of b and f of a, subtract one from the other and get it.
This is capital F, where capital F is an antiderivative of little f.
Okay.
So to get the definite integral of some function, this argument shows you that just find any antiderivative, big F, and look at its, take the difference at the endpoints, and that will give you the definite integral of the original function.
Okay, but either way you can define that.
Yeah, you definitely, you must find the antiderivative.
Okay.
Sarah?
I think you have the prime.
Yeah.
Is the second derivative?
No, so the big F is the antiderivative,
Oh, okay.
right? And then you differentiate the antiderivative and you return to the original function, right? So you have F, its antiderivative, and then you take the derivative of the antiderivative. You come back to the function. Brian?
When on the homework, we would kind of have to like look up the antiderivative and everything. Because they were like very long and complicated.
I see.
That's the book from Wolfram Alpha.
Wolfram Alpha? What?
Well, okay. There's no way we could have figured them out. And then, yeah, the math people ask us to do it. So do you normally look for them?
No.
Really? They still think you know.
Yeah, well, I guess it depends on, depends on how gutsy you're feeling.
Yeah, I mean, one of them was like square root of 1 minus x squared, which like looks innocuous, but the antiderivative is actually like really long and more sign.
The square root of 1 minus x squared?
Yeah.
Yeah, no, I had to look.
The
Yeah, I didn't know
antiderivative.
that one.
I think that there's a trick to that one. So there's a trick to that one that allows you to avoid doing it the way that you think you have to do it.
Could you do it?
Yeah. So what's the trick, right? If you have a function that's the square root of 1 minus x squared, well, what function is that? No. If I say, so let me read it like this. Sorry. What function is that geometrically? It's a semicircle.
Oh, that's for
What's the area of a semicircle? You know what the area of a semicircle is, right? Pi squared divided by 2. Okay.
Wait.
Oh, so you don't need to do the antiderivative.
You don't need to do the antiderivative, right? The question was find the area.
But it asks for it.
It's a trick. It's a trick.
Yeah. So what's the answer?
Like directions.
You don't need to do this. You're such a child picture.
I think the question was, I think, find the area under this graph. But you actually know the area under this graph by.
Oh yeah, that's what it was.
Wait, sorry, what do you mean graph?
Yeah, but we only we only
Oh, there.
Okay.
So how do we find the antiderivative? We can't look it up in books. Something to think about it.
Yeah, I mean, it's basically, what we did earlier. Do you remember we had play this game of, what is, you make some guess and then you sort of fix up your guess. Yeah. So that's what you do at this point. It's basically, do you understand your rules of differentiation, and can you, see how they would go backwards? Right? So if you understand your rules of differentiation, then well, you can generally recognize, oh, this is the result of some differentiation. And then go back. Hey, we'll show you something a little bit better soon enough. Okay. Okay, so going onwards, so 5.3, basic properties of integrals. This section is not that interesting. Sort of things that, so it's sort of like just a laundry list of basic properties. And the problems are also not that interesting. So here's some properties. Here's some of the simplest ones. And I think you can probably tell me what they are without me telling you. So the integral from a to a of a function is 0. Right? Why? Well, because you're taking Riemann sums and the width of the base is 0, right? So you always sum 0. Okay? The integral from a to b of 1 is what? This one's a little bit harder, perhaps. The integral from a to b of 1 is what? Is this a little harder? Maybe it's not harder at all. B minus a, right? B minus a, right? Because you're going to get the area of this block. And the area of this block is B minus a. Question?
Can't you also think of it as the antiderivative of 1x?
You could, yeah. You could say it's the x evaluated between a and b, which is the same thing. Okay. Last one. The integral from a to b of some function plus the integral from b to c of that function, of that same function, is, so I have some function, I have 3 points a, b, and c. I take the integral from a to b, and I take the integral from b to c. And what do I get? Very good. Integral from a to c. Yeah, Victor did. No, yeah.
Just kind of like, so
Yeah.
for the second one,
Yeah.
if it's any constant, the integral of any constant, it's going to be that constant times v1
Yes. Yeah, actually, you're sort of foreshadowing the fourth thing. If you take the integral of some constant, so alpha constant, and you integrate alpha times the function, what are you going to get? Alpha times the integral of the function. Right? Okay. Like if I'm integrating, if I have a sine function, right, and the integral from 0 to phi of the sine function turned out to be 2, right? If I multiply the sine function by phi, then it's the same as phi times the integral of the sine function. So we 10. Okay. You're just scaling the function. And why is that? You have to think about the rectangle. Right? When you multiply a function, you're just multiplying the height of the rectangles, and so you're changing the area by that factor. Right? That's basically everything that we say about these things, about these integrals. You just boil down to facts about rectangles. Next one. The integral of, suppose you have two functions, f and g. The integral of f plus g is going to be, well, again, boil it down to rectangles. Suppose I have one rectangle, and then I have another taller rectangle, and I add them together. What do I get? I get the integral of f plus the integral of g. So this last one is important enough to have a name. It's called linearity. Linearity. That when you that integration commutes with scalar multiplication. And integration commutes with addition, with function addition. Right? You can multiply the function first and then integrate it, or you can integrate, and then multiply. You can add these guys and then integrate, or you can integrate them and then add them. And either way, you get the same thing. So you can do it in either order. That's this word commutes. What this word commutes means. Asha. Is this also a property? Yeah, so these two together, this property and this property together are called linear. Sorry, I should have made that clear. Okay, so basic properties. Let me put in one definition. If we write the integral from b to h, let's just define that to be negative the integral from a to b. Okay, so if I say the integral from pi to 0 of sine, if I say the integral from pi to 0 of sine, what I need is negative the integral from 0 to pi of sine. Okay. We're just going to take this as our definition. Whenever you see something like this, you can reverse it and put a negative sign on it. So it's not. I'm not explaining it, but rather I'm just saying we're going to take this as the definition. Right. integrating from pi to 0, right? That seems, you're starting at pi and you're going backwards to 0. Starting at pi going backwards to 0, we'll count that as negative, the integral from 0 to pi. So there's some sort of negative, basically there's some sort of negative width that you put on it that gives you negative the integral in the opposite direction. Yeah, no.
So you could get like negative area, right?
Yeah,
It's
yeah,
below.
yeah.
How is that like practical?
How is it practical?
Or how is it useful?
How is it useful?
How do you have negative area?
I don't know what to say. I mean, calculus, this sort of stuff is extremely useful in the sense that, physics is based on it. So, I mean, let me say it this way. At least it's a better idea than if you suppose you want the positive area. Suppose you want the positive area. In that case, all you need to do is to integrate the absolute value. Right? You just integrate the absolute value function. Right? And so whatever you want positive area, that's included in this. Okay. So you can, you have your sort of, what you like. You have positive area if you want it, and you have something also a little bit finer, which is just negative area. So we encompass that with this definition. Okay. So let me give you some very dull exercises that are from the book. The properties are not that impressive. The exercises are also sort of contrived. Stop cheering. Okay. So the integral. Okay. Somebody says the integral from 2 to 12 is negative 6. The integral from 2 to 6 of the same function is negative 12. Then what is the integral from 6 to 12? Basically, do you understand the problem? So take a minute. Can you talk to somebody next to you? Okay. So how do you do it? Can somebody tell me how to do it? Somebody explain how to do it. Kelly? Get the integral from 6 to 12. Right? Because you know that the integral from 2 to 6 plus the integral from 6 to 12 is the integral from 2 to 12. Right? So you get negative 6 minus 12. Okay. Let me choose a little one that's a little bit harder. Okay, this is a good one. The integral from a to b is 21. The integral from a to b of f minus 3g is 3. The integral from a to b of 9f minus 6g is 6. What are the integral from a to b of f and the integral from a to b of g? turn to somebody nearby and say, here's what I'm thinking. Or the property that we need to use is Sarah, why don't you talk with the people behind you, Mitchell and Kelly? Okay, so who would like to say how to do it? Who would like to say? First off, what property are we going to exploit? Linearity. Great. Right? So you say, well, look, I know that this integral, like the integral of f minus staging, is the same thing as the integral of f minus 3 integrals of g. I know also that 9 integrals of f minus 6 integrals of g equals 6. So now you're back in junior high school, right? And the question is, you have x minus 3y equals 3, 9x minus 6y equals 6. Right? These are your unknowns, right? You're trying to figure out these things. You know that one of this guy minus 3 of that guy is 3, 9 of this guy minus 6 of that guy is 6. Right? You're back in junior high school and you solve this however you want. I'm not going to do it. You don't want to do you want to do it? Okay, so you've got two lines, right? And you're trying to find the point of intersection of the line. One way, maybe, is to say, well, you say x is 3y plus 3. Right? And then you substitute, you say 9, so 9 times 3y plus 3, and 6y equals 6. That's to say 27y plus 27 minus 6y equals 6. That's to say 21y equals negative 21, and y is negative 1. Okay. Y is negative 1, and so x is negative 3 plus 3, that's 0. So you know that this guy is 0, and this guy is 0. Okay. Any questions? It's just sort of a strange, these problems are mainly just designed for you to check your understanding of the properties. It's not, they're quite contrived. Okay, so let me give some deeper properties of the integral. These are not, all that much deeper, but they're deeper than the ones that we gave earlier. If you have two functions that are integrable on AB, and suppose you know that one of them is always bigger than the other thing, then what am I going to say? Somebody just say it. The integral of the bigger guy will be bigger than the integral of the smaller guy. The integral of the bigger guy will be bigger than the integral of the smaller guy. So, right? If I have somebody bigger, g is smaller, then the integral of that is going to be bigger than the integral of that. Just to make it a little bit more interesting, or right? this is also the same situation. G is bigger than f. Right? The integral of g is going to be bigger than the integral of f. Right? The integral of g is going to be a higher negative number, right? A smaller negative number. F is going to be a big negative number, and so the integral of g is going to be bigger than the integral of f. Okay. Again, that boils down to Riemann sums, right? When you take your rectangles, the rectangles of G are going to be bigger than the rectangles of F, and so ultimately this is what's going to happen. Okay. Along the same lines, if F is integrable on AB and F is bigger than 0, then what am I going to say? Then what can you say about the integral of that? No. It's positive, yeah. So then you know that the integral of f from a to b has to be bigger than 0, bigger than or equal to 0. Okay. In fact, that's sort of subsumed in the previous thing, right? Because you could say, if my function is bigger than the 0 function, then the integral of my function is bigger than the integral of the 0 function, right? Which is 0. Okay. You're all reacting with an appropriate lack of enthusiasm. It's good. It's good. If you were excited by this, I would sort of be suspicious. Okay. The last one. If you know that the integral of f and if you know that f and the absolute value of f are integrable on AB, then what can you say? This one is the hard one, and maybe the most important. What can you say about the integral about their integrals? What can you say about the relation of their integrals? I'd like you to think. I'd like everybody to try to give an answer. So everybody would take 20 seconds and write down an answer. I guess it's sort of hinted. But it's not. I guess it's sort of hinted by the position that I put these things in. But it's not all. Okay, so what's the answer? Okay, I'm going to take a couple guesses. Right.
Is it the integral of f is less than or equal to the integral of the absolute value?
Less than or equal to? Other guesses?
Just less than.
Just less than? What? Equal to?
Wait, I take mine back.
Can anyone say anything more? There's actually something a little bit more that can be said. It's pretty important. The answer is it's greater than or equal to the absolute value of the integral. Okay. So, right, because you know that f is bigger than or equal to f, and you know that f is bigger than or equal to negative f, right? The absolute value of something is always bigger than or equal to the thing, and it's negative, right? So what does that tell you? That the absolute value that this is greater than or equal to the integral of f. It's also bigger than or equal to the integral of negative f, right? Well, if this thing is bigger than or equal to the integral and negative the integral, it's bigger than or equal to the absolute value. Because the absolute value of the integral will be one of these two things. Right? Absolute value of this is either this or this. It's one of those two things. So it's one of these two things, and the integral of the absolute value is bigger than that, bigger than either one of them. So the absolute value of the integral, the integral of the absolute value is bigger than the absolute value of the integral. This might be reminiscent of something. Does this remind you of anything? Linearity? You are using linearity a little bit. Right? You are using linearity with this negative sign here. That's true. But is this reminiscent of anything from a long time ago? Yeah.
Wasn't that theorem that was like the triangle before?
Very good. Very good point.
Yes.
Very good. I'll give you a very good, right? Because the triangle inequality says that if you take a sum of absolute values, the absolute value of the sum is less than or equal to the sum of the absolute values. Right? And this is the same sort of thing. The absolute value of a sum, you see this big S here? The absolute value of the sum is smaller than the sum of the absolute values. This is like the infinite version of that. Okay, so yeah, this is actually called triangle inequality. Where the triangles are, it won't be so evident until maybe later.
Is it integrable? Is it continuous and differentiable? Is there anything else?
So for us, if you're continuous, then you're integrable. But being integrable is a really, really crazy condition. It's that business of no matter what choice of points you make on the Riemann sums, if the partition becomes infinitely fine, you always get the same number. That's what integrable means.
Okay. So you don't have to be differentiable?
No.
Yeah,
All you
that makes sense.
all you need is to be continuous. This function is continuous. It's integrable. Okay. Let me just do one quick example using this sort of thing. Number 33, finding bounds. Okay, so somebody gives you the integral of, we'll do it this way. Okay. So somebody gives you this crazy integral from, say, -1 to 1 of the square root of 1 minus x squared equals. Okay. It says, find the integral, right? Okay. You say, I don't know how to do that. I don't know how to do that. I forget that this thing is a circle. Okay. Okay. So what you could say though is that I don't know how to do this, but at least I know that this 1 minus x squared is smaller than 1. Right? I mean, smaller than 1. 1 is bigger than that. Between -1 and 1, 1 is definitely bigger than that. Right? The max, or you could calculate it using max and mins. The max is going to be 1. The min is going to be what? 0. Okay. Right? Okay. So this is not 33, but it's the same sort of problem. Okay. But then you know that the integral of this guy is smaller than the integral of 1 between -1 and 1, and bigger than the integral of 0 between -1 and 1.
We're doing squeeze theorem.
It's sort of like the squeeze thing, very much so. Yeah. So this would give you 2, and this would give you 0. And although that's not the best answer, that would give you some estimate of the integral that you don't know?
Oh, that can be two.
Because you're integrating 1 between -1 and 1. Like the width of the base,
Oh, okay.
width of the base is 2.
Yeah.
Right. So this is a way, this is, using the results, using the properties we had before, you can get, you can do this sort of game and get an estimate of integrals which are not obvious. Some integrals are not so obvious. The one that I was going to do was this one. Well, what's the integral of this? It's not so clear what the integral of this is. But you can guess, well, its max, this is actually an increasing function, so its min is going to be 1, its min is going to be 1, and its max is actually 3. So you know that it lies between 1 and 3. You have to do a little bit of thinking, but
Did you do that in your head? Can you find min max if you want to?
well, it's an increasing function. It's an increasing function, so the min is going to be the left endpoint, right? So you just evaluate this at 0. That's 1. The max is going to be the right endpoint, so you just put 1 in here, and you get the square root of 9, which is 3. So it's an increasing function. That's all I used. Yeah, clear.
I don't know if this complicates things, but the integral, the antiderivative of 0 could be a constant, right?
Yes, a constant.
Oh, which would be 0.
Yes, 0.
It's a constant minus the master.
Yeah.
Fine.
Yeah. Okay, that's it for today. Next time we'll do the real fundamental theorems of calculus.